how on earth our devices find each other across the massive, tangled web we call the internet? Like when you click a link or send a file, how does that data know exactly where to go among billions of interconnected screens? Well, welcome to this explainer. Today, we're going to unpack the invisible routing mechanics of our digital world. We'll break down exactly how internet protocols work, and we're going to do it using some really clear, straightforward visuals.
So, here's our roadmap for today. First, we'll look at the internet's postal system. Then, the exhaustion crisis. Third, the types of IP connections. Fourth, classful addressing. And finally, we'll wrap up with special purpose addresses.
All right, Section 1, the Internet's postal system. To really wrap your head around the Internet, you've got to frame it as this massive, global network. And right at the heart of its routing system is the IP address. Think of this just like a postal PIN code or a physical home address, but for your digital device. Look at it this way. If someone wants to mail you a physical letter, they absolutely need your home address, right? Well, the Internet works exactly the same way. Without this unique numeric string, the Internet protocol literally wouldn't know where to locate you. That means your computer couldn't send or receive a single file from the web.
Now, this brings up a super common point of confusion, which is the difference between a physical MAC address and a logical IP address. Think of your physical MAC address as the vehicle itself. It's completely hard-coded into the hardware. Your logical IP address, on the other hand, that's the license plate. See, an IP address is a property of the connection, not the device itself. Just like how your physical car stays the same, but your license plate changes if you move and register that car in a totally different state.
So you might be wondering, how did this whole system actually begin? Well, back in the 1960s, a network called ARPANET introduced something called packet switching. Instead of having a telephone operator physically connect a line between two people, data was broken down into these tiny packets and sent independently. But they needed a way to make sure these packets arrived flawlessly. Enter Vince Cerf and Bob Kahn in the 1970s. They created TCP, the Transmission Control Protocol, to ensure the error-free assembly of these packets, and IP, the Internet Protocol, to make sure they actually routed to the correct destination.
Moving on to Section 2, the exhaustion crisis.
Now that brilliant invention from the 70s worked wonderfully in labs, but as the internet exploded in popularity, a massive problem of scale emerged. To really understand this crisis, we have to look under the hood at the anatomy of an IPv4 address. At its core, an IPv4 address is really just a 32-bit binary number, basically a super long string of 32 ones and zeros. Now, humans are notoriously terrible at reading and remembering 32 random binary digits, right? So to make it manageable, engineers broke this string into 4 8-bit chunks called octets, and then converted them into readable decimal numbers separated by dots. This is called dotted decimal notation. It's that classic 192.168.1.1 format you've probably seen poking around your router settings. But here is the huge catch with a 32-bit system. By the strict laws of mathematics, a 32-bit binary number only allows for a maximum of about 4.3 billion unique combinations. That means 4.3 billion is the absolute maximum limit of unique addresses and, by extension, devices that can connect to the internet using the IPv4 protocol. Which brings us to a rather urgent question. What happens when a global population of 8 billion people all need the internet at the same time? And honestly, it's not just laptops and desktop computers anymore. We're talking smartphones, smart TVs, washing machines, air conditioners, home doorbells, you name it. Because of this massive tech boom, we very rapidly outgrew those 4.3 billion available addresses, and that created a very real, very pressing IP exhaustion crisis. To solve this problem, the engineering community didn't just add a few more bits. Interestingly enough, they actually skipped right over an experimental IPv5 and jumped straight to IPv6. And the difference is staggering. By expanding the length from 32-bit to a massive 128-bit hexadecimal format, which uses both numbers and letters, IPv6 skyrockets our capacity from 4.3 billion to roughly 340 undecillion addresses. Yes, undecillion. That is 340 followed by 36 zeros. It is literally enough unique addresses to last countless future generations of smart devices.
Which leads us to Section 3, types of IP connections.
With that kind of infinite horizon in mind, let's take a look at how addresses are actively used today based on security needs. First up, we have the difference between public and private IPs. A public IP is internet-facing and completely globally unique. If you run a business or host a public website, you absolutely need one of these so the outside world can actually find you. On the flip side, the Internet Engineering Task Force, or IETF, wisely reserved specific ranges of IPs strictly for private use. These are used securely inside internal organizational networks or your own home network. They're invisible to the public internet, which adds a totally necessary layer of security for your personal devices.
Then we have dynamic versus static IPs. For most of us sitting at home, our internet service provider gives us a dynamic IP. It's kind of like a rotating guest pass. It changes every time you reset your router or start a new session. It's super efficient for ISPs managing millions of users. A static IP, however, is permanent. DNS servers and major websites absolutely rely on trackable, permanent static IPs. Why? Because when you type in a web address, you need to know the destination hasn't unexpectedly moved overnight.
All right, Section 4, Classful Addressing.
Let's take a slightly deeper technical dive into how the original creators tried to standardize network sizes. To structure these addresses, those 32 bits we talked about earlier are functionally split into two parts, a prefix and a suffix. The prefix acts as the network ID. It identifies the specific, broad network you're trying to reach. The suffix acts as the host ID, which pinpoints the exact computer or device within that network. It's highly comparable to dialing a country code first to route your call to the right nation, followed by the local phone number to reach the specific person.
To standardize all of this, addresses were grouped into specific classes. Take Class A, for instance. The prefix is really small, only 8 bits, meaning there are very few Class A networks in the entire world. But the host ID is massive, allowing for literally millions of computers inside just one network. That makes it perfect for giant global corporations. Class B is for medium networks, basically splitting the bits evenly. And then we have Class C, which most average users and small businesses rely on. It has a large 24-bit network ID, meaning there can be millions of these networks, but each one only holds about 256 devices.
Now you might be wondering about the rest of the numbers. Well, classes D and D round out the pack, but they are strictly reserved. Class D is designated for multicasting, which is sending data to many specific users all at once. And Class E, that's locked away purely for research, development, and future experiments, rather than any standard consumer use.
And finally, Section 5, Special Purpose Addresses. To wrap things up, let's peel back the curtain on a few specific IPs that perform unique, behind-the-scenes jobs on our devices. First up is the loopback address, which is universally designated as 127.0.0.1. Think of this as your local sandbox. If you're a developer and you want to test how a brand new web application runs, you ping this address. It essentially tells the computer to talk to itself, which allows you to safely run experiments on your own machine without ever sending data out to the external internet or risking breaking a live network.
Next up is the broadcast address. This address acts like a giant loudspeaker for a private network. Instead of sending an update or a piece of data to 100 devices individually, which would obviously take a ton of time and bandwidth, a network administrator can just send it to the broadcast address. This instantly reaches every single connected device on that local network simultaneously.
And then we have the link local address. You probably experience this one almost every single day. When you bring a brand new smartphone home and punch in your Wi-Fi password, the router automatically assigns a link local address to that phone. It's basically this instant digital handshake that allows your new device to seamlessly start communicating with your smart TV or wireless printer on the same network.